Yeah, so as I say, I'm Dr. Tao Yang. I'm an assistant professor in the University of Nottingham. Well, it's my second time I come to Chile, and really glad to come here to make new friends, and to communicate our research in the University of Nottingham. In the topic I'm going to talk about, in this workshop, is mainly about the microgrid for the aircraft application in the first 2 days, and then the third day probably talking about the opportunities we can work together. One of my mission came here, of course, to start up cooperation between these UK and Chile universities, and Columbia universities, and another thing is, of course, find good PhD candidates to the UK to study, which is very important for us, I think. Yeah, probably we can go to next slide, if it's possible, or just keep going. Can you go? Yes. So, Marco, yeah, just keep going. It's all right. Yeah. So, I'm from Nottingham. So yeah, for some of you, I think Mark been there for a few times already, but some of you haven't been there. Nottingham is actually north of London. It's about 200 kilometers away north from London. It's about 2 hours by train. Nottingham is very famous for pubs, as I said yesterday. We have the oldest pub in England. It is claimed to be the oldest pub in Nottingham. I'm sure Mark has been there for sure. When you, so if any of you, got a chance to come to Nottingham, I would like to take you guys to there. We have a very good tram system. So it's kind of a way to the electricity, change our lifestyle. So this tram in Nottingham start running in 2016, so very recently. Well, a small town as well. Since Nottingham is about 300,000 people, probably similar size as Grimo, maybe bigger, I don't know. And then this very nice Old Market Square is very beautiful. Normally, at the minute, because it's Christmas, so it's a lot of shops for Christmas. The big Christmas tree. You can do ice skating there as well. Yeah, Robin Hood, of course. Robin Hood is, you guys like to watch movie. I think there's one movie come out recently. Well, 2 years ago, 2 or 3 years ago, talking about Robin Hood. And Nottingham Forest is the football club. It used to be very good in the 1960s, before you guys were born, anyway. And the Nottingham Forest win the Euro Cup. I think Euro Cup for once. So, and now the Forest, it's not that good, but still a lot of fan for the Nottingham Forest. Okay, so Nottingham University, so it's a very beautiful campus. You haven't been there, so there's this Tower building, which when myself started my PhD and postdoc, and about 7 years in the Tower building. Marco is somewhere, every time visit to Nottingham, he probably somewhere stay in this building. Most of the time, probably see the partners in the EU. But when he back to Nottingham, Marco sometimes spend time here. It's a very nice place to work. So the lakeside is actually part of the university. So if you really get puzzled, want to get some fresh air, you just walk by the lakeside. You can do boating as well. So I did, in my 9 years I stayed in Nottingham, I did it once only. You go to pay £5 and you guys spend 1 hour on the lake, which is pretty nice. Yeah, this is the Trent building. It's the main building for the academy, for the chancellor, vice chancellor, and they work here actually. Yeah, so if you guys think about study abroad, you're very much welcome to contact me, contact Gianpaolo, or contact any of us in our faculty. We can sort it out. Okay, myself, quickly go through. So as I said, I studied PhD in Nottingham from 2009 to 2013, and then a postdoc, 13 to 16, and then afterwards become academic from 16 to now. My topic mainly, as I said, focused on aerospace, electric power systems. But there, as I discussed with some colleagues yesterday, so there are lots of cooperation now, well, similarity between the aircraft electric system and the smart grid. I'll probably talk about this later. So the current research topic I'm mainly focused on is one is the high-speed drives. When the machine running very fast, you can always have very high power density, and this is very good for aerospace application. Okay, and then the aircraft power system, we're looking at DC grids. So you're looking at DC converter using dual active bridge, or using and also the solid state power controller. So this is one of the two. If you look at device level, probably these three device level I'm looking at, and also we look at the energy management for the aircraft as well. So which very much linked to the smart grid. So this is the all the projects listed here is what's currently involved in or leading in the EU. So under the Horizon 2020 program, so total volume for about 5 to 6 million euro. This is the figure about put here. So kind of in 2016, I've been awarded as the best PhD in the Clean Sky framework. It's the first year this would come out, which is quite good. Yeah. Okay. So I think just briefly about myself. So today I can probably start to talk about the aircraft electrical system, and then talk about the smart grid, and you can see how these two systems can merge together. So tomorrow I'll talk about a little bit about the stability issues for the smart grid, and afterwards talking about power quality issues in the smart grid. Okay. So aircraft, if you notice what's really going on the ground, you think about 10, 20 years ago, you probably never seen electric vehicles on the roads. And in the past 10 years also, if you notice the automotives on the roads, you see quite a lot of electric vehicles is running. Especially I remember very clearly in front of my office 5 years ago, there's electrical vehicle parking area for charging as well. So 5 years ago, if you go, there was 1 or 2 cars, and now it's every single day is full of electric vehicles. So the transportation application, essentially, what I'm talking about is actually a general trend, and it's really happening not only in the automotive industry, but also in the aircraft level. Okay, so which means you look at the power level of this aircraft is starting from 1960s. Look at power-wise, probably about below 100 kilowatts. But now you look at Boeing 787. Have any of you been on the 787, by the way? Yes. How do you feel? Do you feel comfortable? Like, yeah. But do you feel it's quieter than very quiet? Yeah, no noise. I think it's this. This is why the reason why it's more comfortable or more quiet is because we use a lot of electrical power on board. One of the functionalities which in the aircraft. The aircraft is flying 40,000 feet high in the sky, so the cabin pressure, so the air for keep the cabin pressurized, is the for A320, for example, or 777, they use the air bladed from the engine itself, and for Boeing 787, they use the ambient air and use electric motor to drive the compressor, and the compressor, to compress the ambient air to high pressure and then feed into the cabin. So it's itself, which means we don't have bleeding air, the air from the engine. We use electric power to drive motor and then drive compressor and then supply the power to the the air to the engine. I'll talk about this later anyway. So you see the trend. Essentially, I want to see is the trend of this aircraft or aerospace industry. we are going to have more and more electric power on board. One thing before I move to the next slide, I want to talk about this, which is Pat's little puppy, Professor Pat Wheeler. Probably some of you know him. So within our PMC group, Pat, of course, now the head of the group, and he lead a team to develop this kind of electric racing bike. Okay, so it's completely electrical, and we built the motor. We bought the battery from China, to load the battery from China, and then we put this up, and then this maximum speed of this motor, this motorbike, is 200 miles per hour, and then we win the Euro, what's called this kind of what's the name? Kind of championship in the Eurobike, like F1 stuff, in the motorbike. So we talk about next time you meet Pat, don't forget about it's mentioned this superbike thing. So he's a really big fan of it. Okay. And yeah, this is I think give you an idea about what's really the conventional aircraft you look at. So the main source of the aircraft, of course, from the fuel, and then the main consumer, this kind of engine to use to burn the fuel and produce massive power. And then most part of the power is keep the aircraft in the sky, about 40 megawatts. And the rest of the power is, of course, into 4 different categories. So it can be including the electric power, pneumatic, hydraulic, and this mechanical power. Can I use this also? So the let's speak this way, is that okay? Or because I like to move around, not just standing there. So essentially, so pneumatic power I just mentioned, the environment control system, which for the aircraft application, this is, as I said, is from the engine itself. So the air bleeded from engine, and then to keep the cabin pressurized, and also keep the wing, the aircraft wing, free of ice, which is to keep the aerodynamics good for the aircraft, and also be used for engine startup. So if you go to airport, you find always the noise from the tail, because the APU is called auxiliary power unit, which is a little gas turbine. In the airports, what we do is this little gas turbine produce hot air and to start the engine. And also, this is why you always hear a lot of noise from the tail of the aircraft, because there is an APU unit which supply the air to start the engine. Okay. If you look at the so the hydraulic power, I think we briefly covered this, because I think you guys electrical engineering, but not necessarily specified which area you're going to. So aerospace, that's also probably this is why I want to talk to you a little bit about the aerospace side, because it broadens your vision a bit as well. Okay. So hydraulics system, if you look at the aircraft, you go back to Columbia this time, and the leading edge, the flaps and the rudder, so the rudder is the tail of the aircraft. So there are just 3 movements of the aircraft control. You control rolling, so the aircraft rolling use flaps and aeroline. And then the rudder is control the aircraft going this way, so you call it pitching. And then this is called elevator. The rudder is going this direction. Okay, so the rolling, so 3-dimension movements. So these all controlled by called actuator, and this actuator is controlled by hydraulic systems at the minute. Okay, so if you look at the electrical system for A320 size, it's only 200 kilowatts. It's used for the galley, for the lighting, for the avoiding system. Okay. So this is the electrical devices essentially on the onboard aircraft. You got battery, you got main generator down to the engine. So the generator itself normally is in the engine nacelle. So about the importance of the engine nacelle driven by the engine gearbox. The galley, of course, supply hot coffee, hot tea for you guys in the aircraft. And the cabin entertainment system. If it's a small aircraft, A320 probably don't have this one because the electric power is not enough. But it goes to long journey distance, of course, you will see this cabin entertainment system in the back of the aircraft. Okay, look at this one. This is the called more electric aircraft. I think I talked to some of you yesterday. So the more electric craft is a concept the EU or the US or actually in general the aerospace industry are looking at. The concept is to replace all the pneumatic, hydraulic, and mechanical power we talk about to be electric. Okay, so if you look at Boeing 787, they just follow quite similar structure. So the environment control system, for example, in the Boeing 777 is now completely electrical, and then the wind ice detection, wind ice protection is using the electrical thermomat. So you have electrical power to heat up the wing surface. So what we have, you have a resistance thermal mat, which embedded in under the aircraft surface in the wing, and then use electric power to heat up, like the electric heater, essentially. Okay. So this is the more electric aircraft concept. So you see they have more and more new loads, new electric loads on board aircraft, which means something might to be done for the electrical system above. So we'll probably cover this in next slides. At the minute, the more electric aircraft will have already got products in the market. So Boeing 787, we say, is one of the real more electric aircraft on board. What we are currently doing in the EU, or actually we in the PMC group, in our group, is to look into this, how to electrify this engine, okay? Because still you use the engine itself is the main power source, to burn the fuel and then keep the aircraft in the sky, and afterwards supply power to the electrical system. What we really want to do is use battery, maybe, or use a gas turbine driving a big electric generator, and then supply power to a motor and driving the fan to keep the aircraft in the sky. This is called the hybrid propulsion concept. We're looking at in the H1020 program, or in the with Siemens or Rolls-Royce. This kind of concept. So this is not. I think I'll show you a small video probably. So this is the EFAM project, which is being done between Safran and Airbus. It's a very small aircraft. Its first flight is April, 3 or 4 years ago. I think now it's already in the commercialized periods of the time, and can fly 1 hour and 45 minutes. It does fly across the channel between France and UK. So in April 2014, the pilots actually drive the aircraft from Paris or from France to the UK across the channel. Okay, and they completely electrical, so battery-driven motor, and the maximum speed is 136 mile per hour. 1 mile equal to 1.67 kilometers per hour. So this is about 200 something kilometers per hour. Okay. I think we got some video. Probably you can click to the to this figure. You got pretty good video come out. Huh? So video is just click on top. Yeah, that's it. Just click it. Yeah, should be. Very, very light, actually. Yeah.
Aircraft designer and test pilot Didier Escape gave the aircraft a very thorough inspection. He has flown it before, but not over a large body of water. Even though it was a lovely day, I don't think he fancied a swim. Now the E-fan has two 30-kilowatt electric motors driving 8-blade ducted fans. The motors are powered by 250-volt lithium polymer batteries housed in the wings, giving the plane a flying time of 1 hour. We soon discovered what two surprisingly small thrust motors could do as we were standing directly behind them. Believe me, they dry your hair very fast. Now, one thing I wish we could have experienced was how quiet the E-fan was during takeoff. Sadly, it was impossible to hear anything over the din of multiple helicopters following the plane, but it's obviously a lot quieter than regular planes.
I think I can stop here probably. Yeah. Yeah, thanks. Yeah, so this is very nice. Always like this video. It gives you some kind of idea about how electric engineers can change change everything actually. So this been done 4 years ago. Of course now they call another project called E-fan-X. E-fan-X of course is kind of based on this technology we demonstrated in the E-fan. So try to doing hybrid propulsion, which means they have a A320 style of aircraft. What they are trying to do to take off the engine, one of the engine itself, and put the electric motor and generator on it. So the motor drive the fan, much more powerful. So this something is ongoing, but this one is really flying in the air. So there's a lot of things going on in the aerospace industry. One reason, and towards this kind of direction is really driven by the environmental concern. One of the main benefits of the more electric aircraft or using electric power is, firstly, I think, it has removed hydraulic system. If you remember the conventional way aircraft, you always hydraulic power, but for more electric aircraft, what we try to do is to remove the main pipeline of the hydraulic system, but put the hydraulic system to be localized. This is one way to reduce the weight. And also, as I said, there will be no breathing air from the engine, which means the engine will be more efficient, which is always good for us. And for electric power, always, we can predict. So you got voltage and current. You can always monitor the health condition of the system. If anything goes wrong, you can just reconfigure your system to be more fault tolerant. Okay, so there are 4 pillars for the more electric aircraft. So that's why people want to go for this concept. There's one very strong statement here. So 1 kilogram of the weight saving for a flight for aircraft can save 1,700 tons of the fuel and actually more than 5,000 tons of CO2 emission reduction each year for the whole civil aircraft, traffic, which is I think one of the main reasons why EU and now is so keen on this direction. Okay. Oops. Yes. So the reason why the more electric craft suddenly come to this hot topic, everybody starts to look into this technology, of course, due to the recent advancement of the electric machines. Okay, which and this all from, by the way, this is all from Nottingham University. This all the diagram are from University of Nottingham. So the electric machine, the power converter, and the advanced control. I think these are the key reason why the more electric craft or the electric mobile automotive, all these come into being. So this some project, I think we'll cover this later. This is is a machine converter and this control platform. All this been developed in Nottingham University. So the machine itself designed, manufactured, and the power converter we designed, manufactured, and all this system integrated together and tested in Nottingham University, and after delivered to Safran in France to do the test. Power converter, of course, in Nottingham University is led by Professor Wheeler and Professor John Clare. So we developed this very high power density power converter, 20 kilowatt per liter, this kind of level 10 years ago. So our group, as I said, essentially is really a very strong research group, and in one of the application area we are particularly looking at is aerospace. Okay, and then so we talk about all this beauty of this more electric aircraft and the reason why we want to move towards the more electric aircraft. And just as when we move towards the more electric aircraft, what's really happening is you have more innovative or new electrical loads on board the aircraft. Okay, so this really gives us electrical engineers what kind of impact on the aircraft electrical power systems. Okay, this is something puts a question mark to us essentially, for us to really think about. Okay. So if you look at the options of the electrical and power system for the aircraft, it can be either you stick to what we are doing now, so the aircraft is 115 volts, 400 hertz, or you're moving towards kind of variable frequency, between 360 to 800 hertz. This was actually A380 is using. A380 is using 230 volts. This variable frequency. The reason why you choose to be a variable frequency from this step to this step is to get rid of kind of mechanical complex device essentially. This mechanical device called constant speed drive to change this engine speed, which is time varying, to a kind of constant speed. Okay. And another thing is look at is the DC system. I think this is why if you look at DC, if you think about microgrid, probably there's something similar we can do together. So recently, what Nottingham is really mainly looking at for the aircraft electric system is mainly focused on the DC network. So when we call DC, HVDC here in the aircraft, we're talking about 540 or plus minus 270. We don't talk about kilovolts or 100 kilovolts in the land scale level. Okay, like probably Gianpaolo will probably laugh at me about this HVDC. Actually, it's not HVDC. I mean, every time I talk to industry partners, we talk about HVDC. They always think about 100 kilovolts. I said no, it's only 540 volts. Okay, so this is something very different from airspace and the ground. The reason why it's much lower level because in the aircraft is when it's higher in the sky, this kind of pressure, the temperature will be very different, and this kind of partial discharge phenomenon in the DC system will be very different. So if you go beyond some point, actually the insulation layer will suffer a lot of this kind of partial discharge, and the insulation layer will be damaged quite easily. And we have some research on this as well. Okay. So this is the very quick review of what's really the conventional aircraft looks like. So we always use 115 volts. I think it's quite clearly. Yeah, this is 115 volts AC bus. Okay, and the DC 28 volt DC is always using the transformer rectifier to supply the traditional load, which is 28 volts. The frequency-wise, as I said, is 400 hertz, and then 8 volts is 115 volts, and the power rate is between 200 to 300 kilowatts. If you look at the different aircraft types, A300, Airbus or Boeing companies, so the most fit into this range. Okay, so if you look at, for example, look at A320, you have two 90 kilowatt generator, each generator driven by one engine, and then plus the APU. APU is the one at the tail of this aircraft, and it's another 90 kilowatts. So, it's, for example, for 737, same structure as the A320, it's about 90 kilowatts with the APU to be 90 kilowatts as well. If you look at the Boeing 777, again, if you compare with Boeing 737, it's actually increased about 30% of the power. So it's from 90 kilowatts each to 120 kilowatts each. Okay. Yeah. So this is a quick summary for you guys to to get some feeling of what the conventional aircraft is doing. So we're still so for conventional aircraft, it still stick to the AC voltage to be 115 volts, and then the frequency is 400 hertz. Okay. This is Boeing 787. So this is something I just mentioned. It's kind of first type of aircraft which can be referred to as the more electric aircraft. Okay. Anyway, so you look at the Boeing 787. What's really happening? You got four. Well, it's 6 in total, but each engine is actually driving 2 generators. Okay, and also I mark this out to be a start generator, which means the generator can not only use for generation power, but also can be used to driving the engine for startup. Okay, so as I mentioned, in the conventional aircraft, they use the air from the APU to start the engine, but this Boeing 777 use electrical power to start the engine. Okay, and then the common bus is the main bus is HVAC, so 230 volts, and they have the variable frequency. Okay, so this is 230 volts AC, but it's not 115 anymore. It's a wide range between 360 to 800 hertz. Sorry, and then the environment control system is marked here, so it's supplied by the DC, so transform AC to DC to be plus minus 270, and then afterwards you have a DC to AC converter driving the motor, and the motor driving the compressor. Okay, so this is the environment control system. And the wind heating, I think I discussed with students as well. So using the AC power for the de-icing functionalities. Okay. We still have 28 volts DC. The reason why I have 28 volt DC because this commercialized products, avionics or igniter, or this been a long time as 28 volts. So there's no point to change it because the suppliers will stick to this 28 volts. So there's kind of legacy of 28 volts there. Okay. Yeah. So this is the very brief introduction of this Boeing 777. If you look at the power rating of these generators, about 250 kilowatts. So in total, about 1 megawatt in the normal conditions. Of course, you add into the APU is more than 1 megawatt, 1.5 kilowatts. Okay. This is the architecture we developed in the MOIAD project in Nottingham University. It is a project before the H1020. So we developed this kind of architecture actually at that time for A380 application. So again, we look into the AC bus. Okay. Common, the HVAC bus, and afterwards you have this hybrid architecture. The DC, you have DC bus supplied by the transformer rectifier. You also have the essential bus for the actuators as well. And I think this gives you ideas. Most of the time, we from the conventional to Boeing 787 to even the MOIAD project, we are looking at AC. For the main power system, but there's the one concept now it starts emerging. I think really because the smart grid concepts being caught up by the aerospace industry, and then now we start looking at this DC architecture. So this is the one so MOIAD as is before the H1020. So this one is in the Horizon 20, the Clean Sky 1. So so MOIAD from 2005 to 2007, and this is project we're looking at from 2007 to 2014, and that's we're looking at HVDC bus. Okay, so we got engines driving, each engine driving the generator, and the generator from this AC is cannot see very clearly. So it's this AC to DC converter, and this for the HVDC bus. Okay, and then this bus through DC converter to supply power to the low DC bus, which is 28 volts. So the high voltage bus we're talking about here about 270 or about 270 in clean scale 1. But now we're looking at plus minus 270, which is 540 volts. So you look at the main elements in this system is converter, AC-DC converter, DC-DC converter, and this switches called solid state power controller, so based on Partolyx as well. And then this basically you can see the penetration of these Partolyx into the aircraft electrical system, and then the concept of smart grid, started to be caught by the aerospace industry, and we start to look at the DC grid. Okay, so if you look at this, we go one step beyond. So in Nottingham University, we talk about the common DC bus architecture. This is exactly, I think, reflecting very similar to smart grid. You have a common DC bus, 270, 540, whatever. You have power converter, transform the power, from the machines, AC machines to DC, connect to the common DC bus. You have, of course, on the common DC bus, you have a load, which through the DC AC converter and driving the motor, and also you have batteries as well. In this DC bus, of course, before battery, you have a DC converter, okay, and also you have different loads, resistive load, for example, to do the de-icing application, okay. So this is we call the PV. Apart from PV panel, we don't have PV panel here. We might in the future might have the energy storage like supercap and the renewable energy source, okay. But at the minute, in Nottingham University, we do have this system with this topology. So we've got generator driving the power converter, and then cables to the DC bus. We've got the loads as well. We've got battery, which is supplied by our industry partner from the EU. So we do have this system now in Nottingham University. This is why I can do a lot of research in this area. Okay. So if you guys, in the future think about come to Nottingham to study a PhD, or exchange program to Nottingham as well, if you're working on this smart grid area, do let me know. Okay. All right. So this is the simplified from that topic topology to simplified topology. So again, look at the multiple generation source. So they have three generation systems supply the load, and this is a capacitor, can be a supercapacitor, battery as well. So we're looking at different areas. So one is the power sharing strategy. So using this one using the Joule concept. So we'll talk about this next. And there will be stability issues because all this, if this is the load, okay, there can be generator, can be loads as well. So this kind of driver load or DC converter, which is controlled quite stringently, is essentially a constant power source or power load, constant power load. This kind of constant power loads, you have negative impedance, which give you some stability issues, which something we should look at as well. And also power quality issues. So if you have common DC bus, they have lots of Partolyx, inject harmonics in this bus. How can we make sure this bus is clean? Okay, so the energy-wise, the power-wise, how can we make this clean? Can we use some kind of, because all the Partolyx, they have very good modulation schemes. How can we manipulate or use the different modulation scheme to cancel all the harmonics on this DC common DC bus? Okay, this is something one of my PhD is looking at the minute. This common DC bus concept, when we proposed to Airbus 5 years ago in a committee meeting, so the Airbus say it will never happen. Okay, it's crap, it's rubbish. But now Airbus come to us, say can we start to look at this common DC bus concept? And actually, we had just have a so last year we just got a project from Clean Sky looking into this common DC bus concept. But what will happen is, in normal cases, you have common DC bus, you can everything together, but you do have the SPCs, solid state power controller, sitting between the something in the middle. So if something goes wrong, you can switch off part of the bus. But in the normal conditions, you have the common DC bus always. Okay? This is something very interesting to look at. I think there's something really bring the smart grids and the airspace together. And this is why I think I very much like to work with you, you guys, and share with you some research results we derived in Nottingham University, and you can see if we can find a kind of cooperation point, to in this area, in the smart grids area. Also, for some of you interested in smart grids, this kind of concept, you're very much welcome to you have a plan to come to Nottingham. You're very much welcome to join our team. Okay. I think pretty this is the end of the okay. Yeah, this is a quick summary actually. So, the key message is the penetration of this DC smart grid concept to the aerospace industry. This is very important, the key message. And this is something we can find some common ground between people doing smart grids, use renewable energy, whatever, and aerospace industry. Okay, and what myself is doing. Okay, another one I think probably Gianpaolo will probably talk more about this later. So wideband gap devices, which is also very interesting topic in Nottingham. We're doing using the GaN device. As I said, this DC converter. If we go back to here, this DC converter. We currently what we're trying to do is using the GaN device to build up this converter, and the switching frequency we can go up to 300 kilohertz for the GaN device, 3 kilowatts, not high. But the challenging for this is because this is 270, and this is only 28 volts. So for the device level, 270 to 28, 3 kilowatts, which means current here about 100 amps, and how you can reduce the ripple on this side is quite challenging. And also parallel GaN devices, parallel GaN device is very critical because GaN device by the market is only with low power rating, okay? And how you can connect in parallel is very challenging. I think this I'll probably not present to you this, but I mean we can discuss this after the presentation, okay? Yeah, I think this probably this for the first hour also. I think I stopped here and waiting for the questions. Okay. Yeah.
I have a question regarding the issues in stability by power constant loads.
Constant power load. Mm-hmm.
Yes.
Mm-hmm.
Are you working in solving this from the root control, or maybe a local strategy in the converter with the electrical mechanical actuators?
A bit of both. Because this constant power loads essentially have more impact on the system stability because the active impedance. So one of the methods, of course, look at locally and change the dynamics of these local constant power loads, which means you still have the negative impedance, but probably the impact or this value is lower. Of course, in the system level, you have to be more careful because this give you we will shift all the system the poles of the system to the right panel. Okay, we do actually in Clean Sky 1 we develop kind of stability tool, so we should have. I'll show you on Friday because I think Friday I'll talk very quickly what we are doing. The project-wise we have done so far in Nottingham University in the Clean Sky. There's one specific tool. You can design your system and then input parameters, and press button, and then you can have all the eigenvalues of the system, and you know if it's stable or not. So it's this kind of system level solution. So you develop kind of tool, and then you just using the software to help you calculate the eigenvalue, okay, of the system. Even you have the constant power load. You can see with increase the constant power load, the eigenvalue is shifting to the right panel, which is very interesting. Yeah. I'll talk about this probably on the last day briefly. Give you guys kind of idea what Nottingham University is doing in this area in aircraft research, aerospace related research in the past and in now active projects. So far, if we're talking about funding money-wise, we'll probably have 20 million euro active money in Nottingham, needed by Professor Pat Wheeler, Sergei Bochko, Chris Rada, and myself, essentially. Yeah, so it's 4 of us sharing about 20 million euro. So there's a lot of research opportunities in Nottingham University. And for us, one of the key things, of course, attract the best researchers or students to our group. Yeah. Okay. Any more questions? Yeah.
The power conversion stage, which topologies are commonly used?
That's a good question. For aircraft, only 2 topologies. One is 2-level, another one is 3-level. So far, if you look at 270 and 540. In the EFAN project, EFAN Next project, we are doing with Siemens. So we're looking at the machine-wise to be 4 megawatts for propulsion, and this will be multi-level. So using the modular MMC, so modular converter. So this is depends on the dispatch voltage to choose, because for hybrid propulsion, there's nothing in the market. You can't find it anywhere. This is completely new. So the voltage level completely defined by us, not in university. So we want to define 1.1 kilovolts. It will be 1.1 kilovolts. Okay. I know for the automotive, they are looking at 3.3 kilovolts for the DC bus, and then they are using modular MMC, modular converter, and the level is much higher. But for what I'm looking at myself, we're still looking at 270, or actually we're looking at 540 volts at minute. So looking at 2-level or 3-level converter. For 2-level converter, we're currently looking at silicon carbide based converter. And for the 3-level converter, we look at either silicon or silicon carbide based or hybrid. So one of my students studied thoroughly in terms of thermal losses with different topologies of this kind of converter. And what I ended up with, interestingly, is by using a silicon carbide-based 2-level converter, it's much more beneficial, because you have 3-level converter for aerospace, which you find out you have more power-tronic devices, which means the more chance to get failure. And in aircraft, reliability is a big thing. So you always have compromise between have multi-level or 2-level, because multi-level means more devices, which means less reliability. 2-level have less good, a little bit not as good quality as 3-level, but I do have less devices, number of devices, which means higher power, higher reliability. But another thing, actually, you asked this question, because now people looking at power converter, you're a Portuguese guy, only care about converter. But people really forget the converter is driving the machine, okay? And the converter and the machine should go in together, okay? You cannot optimize per converter and forget the machine, because at the end of the day, you get a very good converter, and the machine cannot operate in a very good way. One of the examples is, if it's very, for power converter, you want to switch very fast, right? You always want to switch fast, switching as fast as you can, okay? For example, for silicon carbide device, we can go to, the current project I'm working at, we switch this 50 kilohertz, or 50 kilohertz using silicon carbide. For some other projects, we try to push to 100 kilohertz. But the problem for that one is the dV over dt. So you switch very fast, okay? And what the machine will see is the line-to-line voltage of, well, the DC voltage on this side. So it will switch very fast, the dt very, very short. And then the DC bias voltage, if keeps constant, 540 or 1.1 1080, what you see is very high dV over dt value, and which gives the machine itself, the insulation layer, the copper, always, the winding of the machine. You have an insulation layer. So if you see a very high dV over dt by this insulation layer, you will, the life cycle of this insulation layer is much shorter. And this is something the Paltronics guy never think about, but because in Northern University we drives, machines, power converter in different projects, we have to consider about the whole system. We have power converter, machine, and the control platform. So we do have this, we do see this problem, and we're working very closely with University of Parma in Italy. So we developed this kind of environment chamber, which allow us to study this kind of dV over dt impact on the machine. So in across the whole EU, there are only 2 universities got these devices, this kind of equipment. It's about 1 million euro equipment. So only University of Parma and University of Nottingham, they've got this kind of equipment to look into this dV over dt problem for drives, essentially. Yeah. I think I talked a lot. I don't know if you get the point. So essentially, for the aircraft, so far we just use two level, essentially. Yeah. Okay. Any more questions? Yeah. No. Okay.
This is a critical application, I think, and in my opinion, fault tolerance should be included in this study.
Yes.
Because
yeah, very good. Yeah. We've been criticized. Yes, with this common dispatch thing. The most criticized, but I agree. Jose, is the fault tolerance. If something goes wrong, what will happen? This is why I think, as I mentioned, it looks like common dispatch. What's really happening is you have SPCs in the middle. So essentially, in the normal condition, this is switched on. But when something happens, this will be open. But we use solid state power controller, so solid state circuit breaker. So which allows, you cannot use mechanical circuit breaker because it's big, and also the time is in a millisecond to break the DC current. But using the solid state circuit breaker, you're looking at microsecond. And this is something we should study. Yes, when something goes wrong, if we switch off this bus in microsecond, will this spread everywhere? Yeah, we do have this study in one of the projects we're looking at in Clean Sky 2. I'll talk about this probably again on Friday. So on Friday, I think I'll give you an overall review of what's the research we're doing in this area. Yeah, so we do looking at it is very critical, and this is why the first time we proposed to Airbus said no, crap, forget it. If something goes wrong, everything is gone. But now, after 5 years development, so all the silicon carbide devices, MOSFET devices, the GaN devices, they are developed in 5 years time quite quick. So now the Airbus start thinking about this concept. Actually, it's quite attractive. Actually, very attractive concept. The only thing is, if the technology allows us to do it, why not? Yeah. So this is the key message. Another thing, actually, I forgot to mention is this hybrid propulsion thing. So there's another project we look at. So instead of you look at these generators, but on this bus you have multiple motor driving the motor fan, and the motor fan provides thrust for the aircraft, so which is which is connected to the called distributed propulsion. So in the microgrid, we have distributed generation system, okay? But for the aircraft, we are looking at distributed propulsion, which means another way around. So it's very similar, a very similar idea. So for renewable energy, you have different power sources spread everywhere, okay? But for aircraft, we are looking at propulsion system across the wing. So essentially, you have 6 motor driving 6 fan on each wing. So you got 12 propeller driven by the electric motor. With one field, I still have 11. Okay, this is a very interesting concept for the aircraft suppliers, because for engine-wise, nowadays you got 2 engines. Okay, of 747 you have 4 engines, but I mean, normally it's 2 engines. If one engine is down, only 1 engine left. But for that distributed propulsion concept, you have 12 or even more propulsion system. So if something goes wrong, still something can be used. So there's, I think, again, come back to the point. For the microgrid, you have distributed propulsion, distributed generation. But for the aircraft, not only have the multiple source generation, but we have the distributed propulsion. So which means, again, you look at the topology-wise, it's the same. So you got power converter and machine. Okay. For propulsion for generation is generator, power converter, machine, converter, and for the motor is converter, machine. So yeah, so very similar. Okay.